In the last section, we had a pretty long refactor of our KNN function. So now it works for any number of features that we try to throw at it. Now, before we test this out in the browser, I made a little typo at some point in time in the last section. You'll notice down here on two pairs, I accidentally at some point put the underscore dot right there. Don't know where that really came from, so I'm just going to clean that up really quickly. Okay, so that looks better. Now I'll go back over to my browser. I'm going to refresh the page. It looks like everything is still working. Okay, so just as before, our application is still set up to do some analysis for our k values. That's totally fine. We're going to now do the analysis for ideal k values using these multiple different dimensions. So maybe with multiple dimensions, maybe we'll find out that our k value that is optimal is going to change. Who knows? Let's try running this and see what happens. So I'm going to again do 10 different balls at 10 pixels. So I'll do my drop. I'll do another drop, and one more for good measure, and then I'll run my analysis. Okay, so let's see how we're doing. Okay, so everything is printing out just as it was before. You'll notice that it's significantly slower this time around. The reason that it's so much slower is that we've added in quite a bit of complexity by including multiple dimensions. Some performance issues like this is something that we're going to be really concerned with later on inside the course. But for right now, we're just going to kind of suffer with it running a little bit more slowly. All right, so I got my output right here, and it looks like in some cases, our accuracy is way better than it was before. Now, I'm kind of surprised that it's so much better. You might recall that before for a k of 1, we had something like, 0.2, and a k of 2 is something definitely like 0.2 as well. So maybe I'll try this one more try. I'm going to refresh. And I'll do 10 on 10 again. And one more, and I'll run the analysis right away. Okay, there we go. So again, I'm going to print it out. And again, it still seems to be quite high. Seems like it's doing awfully well. That's definitely not the worst thing in the world, but I want to point out something to you that could be throwing these results off and maybe not adding in that bounciness factor quite as attractive as these results right here would make you think that it is. So let's take a look at a diagram or two. Okay, so as you recall, let's see, we're just looking at this one right here. We had said that we were going to plot our drop position against our bounciness. And then on our axes, I had ranges from 0 to 200, 400, 600. And then on the bounciness, we had 0.5 and 0.55. Now the way in which I made this diagram right here was very, very misleading. I want you to look very closely at these axes. The x-axis, or the horizontal one, is running from values of 0 up to 600. But on the horizontal, or vertical, we're running from values of 0.5 to 0.55. But I still made it seem like the gap between these two values right here was identical to the gap between values of 0 and 600. Let's take a look at another version of this chart that is going to be graphed a little more realistically. Okay, so this one is a little bit more realistic. It kind of accounts for the true distance or the true range between the different values of bounciness and the range of values in our drop position. You see, as the drop position starts to change, we're getting very large differences in our numbers, anywhere from 40 to 150 to 425. But as our bounciness changes, it's only going from 0.5 to 0.55. So in reality, all these data points are essentially on a straight line going right across. What does that really mean? Well, it means that when we start to do our analysis, the bounciness factor is probably not affecting anything quite as much as you might expect. If we try to find the distance of points, or try to find what points are close to our prediction point right here, this diagram makes it seem like maybe point B is the closest, or this green point right here is the closest one. But in reality, if we really consider it from the correct axis perspective, that green point is not the closest one. It was this one over here. Oops, that one right there. Because the bounciness factor is very, very small. So small that it might as well be 0. If you even look at this equation right here, you'll notice that the bounciness term ends up being 0.03 squared. Which is a very, very small number. Let's actually, run the math on it very quickly. So the bounciness factor is only 0.03 squared, which is 0.0009. Very, very small. But the distance calculation was 350 minus 323 squared. Let's make sure we get our parentheses in there. And the result of that was 729. So what that means is that the contribution of distance from our drop position is a huge, tremendous factor compared to the contribution of our bounciness factor. It essentially means that the bounciness is just not in any way contributing any meaningful information to our k-nearest neighbor analysis. So clearly, even though we've wired this thing up to use multiple features, it's maybe quite not working the way we expect. So let's take a quick pause right here. When we come back in the next section, we're going to talk about how we can kind of address this problem and solve the fact that the bounciness seems to be such a tiny little factor. Okay, quick pause and I'll see you in just a minute.